The problem that we're looking at here is we have three cables, AC, BC, and DC, which are acting to support that block there of E. What we know is, in a symbolic form, we know the tensions in cables AC and BC. And what we want to do is talk about the forces that those cables act on block E. So for example, we're talking about the tension force of FAC here. It acts from C to A. Then the force BC is acting toward B. And we want to be able to first project FAC onto cable CD and then project FBC onto cable CD. In the end, write these projections as vectors. Our first task then is to find the unit vectors for our three cables. For cable CB, the unit vector I'm going to write down is from C to B, the same direction as the force. So that's going to be going from C to B. The distance, that's going to be 5d in the y direction. It's going to be 2d in the minus k. And so to make it a unit vector, I divide by the magnitude. So that's 5d squared plus 2d squared. And that unit vector, therefore, becomes 5 divided by the square root of 29 in the j minus 2 divided by the square root of 29 in the k. The unit vector I'm going to draw there for CA, that points from C to A. I go the distance from C to A, so in I I'm going minus 3D. In J I'm going positive 5D. And in the Z direction I'm going a positive 2D. And again, dividing by the length, that gives this a division by 3D squared plus 5D squared plus 2D squared, and take the square root. What I end up with is minus 3 divided by the square root of 38 in the I. I've got 5 divided by the square root of 38 in the j. And in the k, it's 2 divided by the square root of 38, like that. And lastly, for cable CD, I'm going to choose to write that unit vector from C to D. And so the distance, going the distance between C and D, I go 3D in the positive x, I go 2D in the positive y, and I go 2D in the positive k, dividing by the length. So I divide by the square root of 3D squared plus 2D squared plus 2D squared. And so in the end, I am looking at 9, 4, 13, so that's 17. So that's 3 divided by square root of 17 in the positive x direction. I'm going 2 divided by the square root of 17 in the positive j, and k is positive 2 divided by square root of 17 in the k. So those are our three unit vectors that we're going to need. For part A, we want to take the force, which I've designated there as FAC. I need to project that onto ECD and multiply by ECD. So that's going to be the tension force there, TCA, the given, ECA, dot it with ECD, and follow that up with a multiplication of ECD. So that's that tension force of TCD. The first dot product is going to be I guess I should probably write this out to make sure I don't make any mistakes here. That's going to be bring out the square root of 38 and the square root of 17, and the dot product is going to be between minus 3i plus 5j plus 2k, dot it with ECD, and so that's going to be a 3i plus 2j plus 2k. Again, I'm multiplying by ECD once I get through. And so what I'm going to end up with then is going to be TCA square root of 38 square root of 17. So that's going to be a minus 9 plus 10 plus 4. Then it multiplies by ECD. So ECD in the end is 3i plus 2j plus 2k, and that gets multiplied again by the square root of 17, so that is going to be a squared here, and this number of course is going to be equal to 5. So that is our projection for the first part, for part A. The projection there for part B, I take the force that's carried by member CB. So this is F. What did I call it in my picture here? FBC. I dot that with ECD, the unit vector. ECD. So that's going to be the tension force there of CB times ECB. Dot it with ECD. And to make that a vector, we follow that up with a multiplication by ECD. So that's going to be tension CB. And I will end up with, well, I guess I should probably write it out just to be safe here. Let me take a peek at that. That's going to be divided by the square root of 29. And that's going to be 5i, I'm sorry, that's a 5j minus 2k. The unit vector, that is going to be a 3i plus 2j plus 2k. And I have the square root of 17 that comes out of that. So that's TCB square root of 29 square root of 17. When I dot these through, I get no contribution from x because there's no x in the force. So what's left here is a 10 minus 4. Then multiply that by the 3i plus 10j plus, 2j plus 2k. And along with that comes another scale factor there of square root of 17. So this becomes a 6. So problem came down to writing out unit vectors for each one of our three cables. For CA and CB, we needed those in order to write the forces. And since both of those forces are projected onto the direction of CD, we needed the unit vector for that. So those unit vectors were taking the position vectors from those 2 points, as we usually do, divide by the magnitude, and that gives us with vectors of length 1. The first projection, FAC onto CD. Second projection, FBC onto CD. In each case, again, the question asks for the vector projection. So in the end, we multiply by that corresponding unit vector to signify the direction in which that projected component will act.